cycles and their mother.
Yeah. Thank you for inviting me. I'm really happy to talk here and to meet all of you. So, so I'll talk about computing Motivic nearby cycles and their monodromy. This part is joined with Emil Jacobsen. And there, I wasn't sure if I don't know if the monodromy of the cycles or of the sheaf, but they, I guess, is pronoun inclusive enough, so it's there. So the general setting that we work in is we have a map F over a base, map of schemes, which is flat and quasi-projective. And I'll draw a picture. So this is the base S. In the base, we have an open and closed complementing subschemes. So this is open and this is closed. With this being what we call the generic fiber, and this the special fiber. Okay, F sigma, F eta. And usually, or at least in this talk, S will be the spec of a DVR. And then this is a generic point, the spec of the K, which is the fraction field.
Do you think that this is Hantarian?
At least in some of the results. So sometimes it will be also strictly Inselian even, but not always. And this is the closed point. The spec of the residue field. And we also assume that this is smooth. And say that X is regular. Now, in this setting, Ayoub defines the Motivic nearby cycles, which is a functor from SH of X eta to SH of the special fiber. Yes, in the setting of SH, so I think that this category was already introduced today. And what is it and how is it defined? So first, maybe it is not, I won't say much about how it is defined, but it is not, let's call this J and this I, So it's not I star j star, although this one is also a nice functor between this category that is usually called chi f. I just try not to use it because I also use chi for the Euler characteristic. And anyway, this is not this functor. But then in the et al. Case, well, instead of SH, there's the derived category of bounded complexes. So in the et al. Lehalleur case, one can lift the generic point to a geometric point. Eta bar, and then so the spec of K bar, the separable closure, and consider J tilde instead. To X S bar, well, S bar is the normalization in eta bar of S, and then take maybe I tilde star J tilde star. But this is still not this psi f in the Motivic setting. So no, I said we have this functor.
Yes.
So I just gave a possibility to define a factor, and I said this psi is not this functor. That's all.
Formalism on
Yes.
instead of a Cauchy, you still wouldn't get the psi even in that case. Okay, just mean that the copy this definition into that setting is not the exact. Okay.
Okay. So in SH, I won't say what it is, but I will just say that the construction goes through first upsilon f is constructed, which is the unipotent nearby cycles. And then through some colimit of finite covers, psi f is constructed. Well, and how is this constructed? So Ayoub defines some co-simplicial objects which models paths from GM to the point, more or less, and uses this. Well, so then somehow we have this functor, and we'll talk about some basic properties of this psi f, which also apply for this functor and also apply even for this functor. So some properties. So first, if H from Y to X is smooth, we have an iso like this. And if H is proper, we have an iso with push forward. So just some example, we can start doing computations with the formal properties. Then say from here, if H, if we have H proper and H eta being an iso, then psi f of 1 is the push forward of psi fh of 1. So maybe we can use h to make it more computable and then push forward. So I'll make some definition. So let G from Y to S be finite type flat morphism. Then we say that G is semi-stable if X sigma is a reduced normal crossing divisor. We can write, Y sigma. We can write Y sigma as a sum of, say, the eyes which are smooth and intersect well. So this is one definition and another definition, which are not necessarily the standard definitions. I think there are some variations between sources. So at least for this talk, say that f from X to S admits semi-stable reduction if there exists a natural number denoted by S prime, the extension of adding if root of t. Okay, I didn't say what t is, so t is a uniformizer in O. And H from Y to X E, which would be this base change over S prime, such that G, which is this composition, is semi-stable. And H eta is an iso. Well, then, no. Then, and using the formal properties of this functor psi f, we get some key, what I'll call here a key fact, which is a theorem by Ayoub, saying let G from Y to S be semi-stable, and write Y sigma is this sum of the i's, and the I circle as the I minus the other components. So we have an open embedding of the I circle in the I, which I denote by V. And the I is a closed component of X sigma, which I denote by U. Then U star psi f eta upper star is isomorphic through the unit map to V star U upper star psi f eta star. Now, yeah, thank you. Yes. Proper. Thank you. Good. So what it means that to compute this restricted to any of the components di, we can restrict to these smooth parts without the intersection and compute it there. And yes, I was trying to use G for the semi-stables because we reduced, but yeah, it wasn't a good idea. So yeah, so everything here is G. Okay, so just as an example of how to use it, if we try to compute in that case psi g of 1 restricted to di, we can take, it would be v star of psi g of 1 restricted to di circle, which, since this is smooth and we have also the smooth pullback property, it would be the same as V star of taking the pullback all the way to the base to K, or say to sigma, and then pulling back with psi id of 1. So if we know this, which should be 1, at least in characteristic 0 it's 1, then we know this. But this theorem is true for any specialization system, so basically also for all the others that I mentioned. So how can we use this to compute things about psi? So I'll give some examples. Let's see.
So is there really a problem with the psi identity not being 1 in positive characteristic? Is that unknown, or is it false, or is it?
It's always 1. Yes. Okay. Yeah. So it's always 1. Good. Okay. Thank you. So let's see. So maybe I'll just now mention a few results that compute the nearby cycles and use this key fact. So I'm short on time, so I'll just say that there's for example, one example which I won't write down, there's a result by Ayoub, Vora, and Sebag that compute the class of psi f of 1 in the Grothendieck ring of varieties, and show that it's the same as the Milnor fiber of Denef and Lozer, which I may not say much about that, but let me say something else. So the first thing that I'll talk about is the quadratic Euler characteristic of the nearby cycles. So the Motivic Euler characteristic was also introduced today, so that's good. So if P from X to K is finite type, K is a perfect field, the characteristic is not 2. Then we have the Euler characteristic, the quadratic Euler characteristic with compact supports, which is the trace of the identity of the motive with compact supports of X, which is an element in the endomorphism ring of the unit of SHK, which, as we saw today already, is an element in the Grothendieck with a ring. So we have this. This is dualizable object, so this makes sense. So let's start with the theorem. So with all the assumptions above, have f from x to s, and p in x sigma, an isolated singularity such that in the stock of the point, we have that f star of t is f s0 to sn plus age, with S0 to Sn being local étale coordinates, and f being homogeneous polynomial of degree e, and age having degrees higher than e, in the expansion. So if we are at this situation, then we can compute, and well, the exponential characteristic of k is co-prime to E, but f defines a smooth projective hypersurface, then the Euler characteristic of psi f1 restricted to P is the Euler characteristic of this thing, f t0 to tn minus tn plus 1 to the e minus 1, the Euler characteristic of f t0 to tn. Also v. So this is v in Pn plus 1, and this is v in Pn. And what's the idea of the proof?
So can you say again the assumptions on S? Can it be a mixed characteristic?
No. No. It's the same characteristic. I assume that K embeds in O. So the idea of the proof is the following. So we want to get a semi-stable reduction for this f and then use this key fact. So semi-stable reduction is achieved by base changing to S prime after adding an if root. Oops. Then blowing up at P and normalizing. Then, if we just do this, we can compute what special fiber we get. So we get G from Y to S prime with Y sigma having two pieces, one coming from the exceptional divisor and the other from the strict transform of the special fiber, with D1 being this V of F T0 to Tn minus Tn plus 1 to the E. And C, which is the intersection, being V of F. Now, let's do this. Okay, so now just using the localization sequence, you can get the result. Yeah, we have C in D1 one circle. Here we have a localization sequence that will give us that chi of psi f1 at P is the same as psi g of 1 at D1, which is by Ayoub the same as this V. This is V star of this, which by the localization sequence and the cut and paste property of the Euler characteristic with compact supports, this would be chi of D1 minus 1, which comes from a GM twist here, and this. And then we get the formula. So, what is this good for? So, one thing is that as a corollary, and using, we can extend the formula, the conductor formula, of Levine, Pepin Lehalleur and Srinivas to a proper f from x to s in characteristic 0 with singularities as in the theorem, with isolated singularities as in the theorem. Okay, so I'll say that quickly. So the formula looks something like this. Say that the singularities are P1 to PR. They have different degrees. So I'll explain what we see here. So this is the quadratic Milnor number, which can be defined as some quadratic, some bilinear form on the Jacobian ring. And this is what Jonathan mentioned as a multiplicative and additive additions to the Milnor formula. So if we take ranks to get the complex, the original Milnor formula, then they disappear. This becomes -1 to the n. And this is the formula. So the stages is, I think that LPLS proved this for, and this SPT is from Grothendieck bit of the field K to Grothendieck bit of the residue field K, sending the quadratic form T to 1. So LPLS proved this, proved the formula. For, let's call it XH, which is the quadratic hypersurface F minus T, Tn plus 1 to the E, going to S, let's call it FH. And they also proved, summarizing it, that this SPT is the same as the one induced by psi ID. This is the same as the Euler characteristic of psi f of 1. I just stopped writing the C, but it's still the compact support one. And then I proved the theorem that I just told you, together maybe just with a comparison of those quadratic. Yeah, just it's technical that f pi is the same as the quadratic Milnor number for this fh, and the singular point there, which is whatever it is. Let's call it O. So, yeah, adding all those points up, using the computation there, we get the same arguments as in the formula that they proved. This gives the required generalization. Okay, so that was about the quadratic Euler characteristic of nearby cycles.
Sorry, I have stupid question. So, question
Sure.
is about, would you like to explain the reason you use like S prime? You every time you like you base change to S prime, and then you can reduce the thing to semi-stable case. I mean, would you like to explain some geometry equation about this construction?
Yes, you must let's see. If I just blow up, I get the exceptional divisor has multiplicity, which is the same as the degree of the polynomial. Now, for the semi-stable reduction, I want it to be reduced. So the only way to do that is I have t there, so I have to take this if root of it. Good. So the other computation is about computing the monodromy. And this is work in progress with Emil Jacobsen. Okay, so first, what is the monodromy in the Motivic setting? So, working with Q coefficients, Ayoub constructed a unipotent monodromy functor from this epsilon f twisted by -1. Maybe I should have said just that I didn't, that this is not the most general form, because the residue fields at the points can be different, and also instead of a homogeneous polynomial, it can be a weighted homogeneous polynomial, which makes the construction a bit more complicated, but along the same lines. And this is, as Jonathan said, it's an extension or some variation on the Deligne-Milnor conjecture, which appears in SGA 7 Exposé 16. So this is more like SGA 7 Exposé 15. The Picard-Lefschetz formula. So, so he constructed this. So again, maybe I'll tell you quickly about the L-adic, what happens there. So the L-adic setting, say that O is strictly Enzelian. Then we have an actual group, the Galois group of eta bar over eta, operating on psi f in this case. The étal psi f, not the Motivic, of the constant sheaf. And then for f semi-stable, the action of I factors through this Tate module, such that if we take psi to be a topological generator, we can define some map here, which I called n psi. Composing with psi minus 1, I get this. So this is kind of logarithm of the action. And then I get this n, which is the monodromy operator. So the Motivic monodromy operator generalizes this. I may say a bit more about how this is construction in the end if we have time. But our aim is to compute this for a homogeneous quadratic singularity. So aim compute n for a quadratic singularity, but not only. There's still room for improvement in operating these blackboards. So, so the first case as before, G from Y to S is semi-stable with Y sigma of the form D1 plus D2 and C being the intersection. And again, we have C in D1 circle. We'll say this is V and this is I. And then there's the localization sequence, I star, I upper shriek, 1C, 1D1. Yeah, this is from the 6 functor properties in SH, or actually DM in this case. So then in DMQ, which is where we have this n defined, we have get the following triangles. Yeah, we get this just from here and from using, again, the key fact. Yeah, so plus key fact that this V star of 1D is psi f of psi g of 1 restricted to D1. That's how we get psi into the story. So this is one triangle, and there's also the dual triangle, which looks this way. Now let's denote this by A and this by B, and try to describe the monodromy. Okay, I forgot to tell you some maybe defining property about the monodromy. It fits into a triangle. So there is a triangle. With this functor I star j star, which then this so this is a natural map of the between those two specialization systems, and N becomes the map to the cofiber in this. Okay. And the reason that I exchange here upsilon with psi is that in the semi-stable case they are the same. Okay, so we have this, and let's see. We have the unit map along C. Okay, I also didn't tell you what this C is. Sorry. So, we have C, D1 D1 is in Y sigma, and this embedding is C. I also denote it by C. And then I have C lower star, C upper star, psi G of 1. This is the unit map on which I can apply C star of A to get C star 1 minus 1 minus 1. So this is C star of A. Now the fiber of this turns out to be 1. And the fiber of this is this I star J star of 1. Where this maps to this. Meaning that these n factors through this composition, but we can also do the dual thing. So here we have C star C upper shrik, psi G1 minus 1, and here C star 1 minus 1 minus 1, where this is C star of this B, twisted by minus 1. And it also factors through this. So we have this, and then we just... Okay. So we just determined the monodromy up to an endomorphism of this motive. Let's call it alpha. And now what do we have left to do? So maybe 1 is to compute alpha. And in fact, alpha equals minus 1. That's the answer. And 2 is to reduce or descend to the case that we wanted to consider from this first case of G. So descend to F with, say, a homogeneous, isolated singularity. Now I have I'll describe how to do 2, and then I hope that I'll have time to say something about 1. So, how many? I have about 2 minutes. 2 minutes. Okay, so I even won't have time to say something about 2. So, well. So, okay. So I don't have much to say about 2 because it's what we did already also in the previous case. So let F be as in the previous theorem. To make it quick, then the same construction, of G from Y to S prime. Well, we get Y as we wanted with those two pieces. Well, D1 is the fiber of this point P. We have Y sigma and X sigma. And then the monodromy looks that way. So the minus comes from the -1, so I won't have to write this. I put minus. And E is just for the base change, it just divides by E. So after writing E here, I can replace F with F prime after the base change. And then it decomposes the following way. So epsilon F of 1. Let's call this O. O star O star of epsilon F of 1. Then the push forward to 1C minus 1 minus 1. Then O star O upper shrik, epsilon F1 minus 1, epsilon F1 minus 1. Now, these can also be computed using the key fact and this square. So this is taking the push forward from D1 circle to X sigma lower star of 1 D1 circle. And this is the same just with lower shrik. So we get something, maybe to write it again. This is the motive of D1. This is the motive of C. This is the motive with compact support of D1 circle to here. This is the monodromy. So this is what I call the abstract Picard-Lefschetz theorem. But also we computed in the previous case what are those C and D1 circle. They are still the same thing. So this is quite explicit. And for the degree 2, for the quadratic case, I think that we can also compute them more explicitly in the MQ. Including the maps between them, for example, to show that for n even, this is the monodromy is 0. So this is it, and yeah, I think maybe the harder part is to show that this alpha equals -1, but this can be done using the construction, one construction for this epsilon f, which I didn't tell you about, which I think it's called as a polylogarithm. That's how Ayoub defines this n. So we take, can I just have 2 more minutes? Okay, so I just write it here. For 1. So we have the Kummer motive in, say, SH or DM of GM, which is an extension of this sort coming from some natural map where K is defined as the cofiber. And then this upsilon f equals I star j star of something called log, where this log is infinite symmetric powers on this K. That's where we need the Q coefficients. If we have another construction for this n, maybe we can get rid of them.